大家好，我今天想告诉你们对物理学里面很重要的概念、很重要的原理。Hello, everybody. Today I want to talk to you about uh, one of the most important principles in physics and in mechanics, particularly, called Newton's first law. So, the topic for today is Newton first law. So the law establishes a relationship uh, between two quantities. So I'll first write the law. On the left hand side is a symbol F is equal to product of two things. So it pays off to take the time to understand what the terms of the equations are. So on the left hand side, there's F. Now, F stands for the force. But as you can see, above F is a little arrow. So therefore F is actually a vector. On the right hand side, there are two terms. That's true. M, which stands for the mass of an object, as if the mass was all concentrated at the same point, the point mass of an object, we call it, times, and here's A, the symbol A, which also has a little arrow above it. Therefore, A is also a vector. So the law really relates two vectors, relates two quantities, a vector called the force and a vector called the acceleration. And the relationship happens to be linear. And the relationship is that the force is equal to some quantity, the mass of the object, times another vector called the acceleration. So this one is the acceleration. And this one is the force. So in terms of the meaning of the law is that to a point mass, an object whose mass is all concentrated in a point, and the mass being m, if I apply a vector force to it, then I will cause its acceleration to be in a linear relationship with the force. That is, if F is applied to an object, then it will cause this object of mass m to accelerate. So let's consider a very simple example, a one-dimensional example. Now, I draw the mass here as being extended, and but in fact it means all the mass is concentrated at one point, and the motion is constrained along the x direction. So x is measured here. If a force F is applied along the direction of x, then it will cause the object to accelerate along the direction of x, or along the direction of the force, that is to say. It's such that the acceleration that will be caused will be given by the force divided by the mass of the object. And I remind everyone the meaning of acceleration. The acceleration is defined as, since I'm not sure whether you have a background of differentials or not, I will write it in terms of differences. It's defined as the change of speed over the small change of time. This is true in the limit of delta t very small. So in other words, it will cause the speed of the object to change. I want to talk a little bit about the concept of vectors, because this is very important. I mean, since I'm not exactly sure what you guys have in your background, but so it doesn't hurt to just remind ourselves what the meaning is. So a vector is a quantity that has two attributes. Number one, it has a size, 도다. How big is it? And number two, it has a direction, xiang. So vectors are interesting objects, different interesting concept. It's not a simple concept because it has how big is it associated with it. But not only that, it matters how big is it towards what direction. So this is why we use in mechanics or dynamics an arrow to determine to signify what a vector is. It has a size because the arrow is a certain length in a direction. So in a XY coordinate system, assuming that it should have drawn it starting at the origin to be more exact, then this vector points at an angle theta above the horizon. So in order to make sense out of it, we usually resolve the vector into directions. So by projecting along the axis, it has two directions. The this, let's say we call this F, then Fx, the x component of the force would be F, the modulus or the size of the force times the cosine of theta, whereas the y projection, it would be Fy is equal to F times sine theta. Now a scalar scalar has only one attribute, one defining notion to it: size. So the mass is such a thing, is a scalar. And the acceleration is a vector. Remember, the acceleration is the change of speed, which is also a vector divided by the change in time. As delta t, the difference in time, it gets very small. Which, by the way, for those who know differentials, is dv dt. So to recap, the force establishes a relationship between two vectors, f and acceleration. And the relationship that is established is that it's linear, and it depends on a property of the object called the mass. Now we're going to talk a little bit more about that in a second. I want to talk now about an important concept related to Newton's first law. So again, F is equal to m times a. The issue is that you will encounter in physics books and throughout the discussion of Newton's first law, you will encounter the following terms: so-called inertial mass and so-called gravitational mass. So when an object is, say, on a surface like this, a plane surface where gravity is the same everywhere, so it doesn't enter into the discussion of the problem. Let's say there's no friction. So this is x. You apply a force and you cause this mass to accelerate. Well, the acceleration that will be imparted will be F divided by the mass. The mass you're going to use is so-called inertial mass. But the issue is, how do you measure mass, right? You put this mass on, well, I mean, you could measure mass by just measuring the force and measuring the acceleration, and therefore taking the ratio of the sizes, and you would get the inertial mass. That would be one way. But if the object is subject to gravity, then some object of mass m, again, is acted upon with gravity such that it accelerates with the gravitational acceleration, g, we call. And so this is caused by some force that's acting on it, obviously, otherwise it would not accelerate. And that's the concept of weight. Well, this force, this mass is known as the gravitational mass. Now, there are not two masses because the two are identical. That is to say, the object only has one mass. It doesn't matter what kind of force, whether it's gravitational or mechanical, applied to it. But for those of you who want to think about these things a little more deeply, you will think that it is quite interesting to see that the gravitational mass is actually equal to the inertial mass, because gravitation and the concept of applying a force to an object are two different things altogether. So it is important to know that there are these two concepts called inertial mass and gravitational mass. But in fact, there's only one mass, that is the mass of the object. The two are absolutely identical. Okay, now I want to talk about units. So again, the force, a vector, is equal to the mass, a scalar, times acceleration. So the unit of force is called the Newton. So I think I have learned in classical mechanics that you write units like this. This means the units of force is equal to the Newton. There may be a different method using the new system, the system that's being taught. So I'll use that new notation when appropriate. The mass is measured, the units of mass are kilograms. Kilograms. And the units of acceleration are, well, what is acceleration? The acceleration is the change of speed per unit time. So meters per second change per second, so meter per second square. This always confuses students. Acceleration is the change of speed per unit time. So speed is measured in meters per second. So speed change per unit time is meters per second. That is, how much did they change per second? How much does the speed change in meters per second each second? So per second squared. If this is still unclear, we can talk about it offline. So anyway, the Newton is equal to 1 kilogram times meter per second squared. So those are the units of force. Okay, so now I want to talk about something that some of you may have already noticed about Newton's first law, which is very interesting. F, okay, is equal to m times acceleration. Well, we said that acceleration was equal to the change of speed per unit time. So we could write this as m times, and I will write it in terms of differentials here, delta v over delta t. Here v is a vector. We always, it is implied that delta t is very, very small. So we say tends to 0, delta t. So the time difference at which you make the measurement and change of speed is very, very small. So anyway, so this is a very interesting equation, because since the mass is a scalar, you could easily stick it in the change, past the change, right? It doesn't matter that the mass is outside or inside the difference. So you could write this as delta m v over delta t as delta t tends to 0. But mv, as we know, is the momentum. Remember? M times, so the momentum is another vector is equal to n times v. So interestingly enough, F is equal to delta momentum over delta t. So another way to think about the force, if for those of you who want to think about the force in terms of what does it cause? It causes a change of acceleration of a mass, and therefore a change of speed. But another way to think about it is it causes a change of momentum. So when you apply a force, you change the momentum of the object of mass m. So we say that F is delta p over delta t in the limit that delta t tends to 0, which, for those who know differential, is dp dt. So this is a very interesting and important concept. I want to talk about particular situations that will be instructive into getting more insight into the situation. So let's consider that the motion is frictionless, no friction, and it's constrained along the x direction. I write 1 sub x with a little bar over it. That means unit vector in the direction of x. And there's a mass here that moves under the influence of a force that acts along x. So force is parallel to x. And we just learned that this causes the acceleration of the mass to be equal to F divided by the mass. Another way to look at Newton's law. So the force causes the mass to accelerate, which is acceleration is the change of speed over time, delta v, delta t. So the force causes the mass, the speed of the mass along 1 sub x to change. Now consider the situation where the mass is moving at a constant speed, v, along 1 sub x, along the x direction, no friction. What is the conclusion that you can draw from this? Well, if v is equal to 0, I'm telling you v is equal, if delta v over delta t is equal to 0, that is, v is constant, delta v over delta t is equal to 0, which means the acceleration is equal to 0. And if the acceleration is equal to 0, this means that the force acting on it is equal to 0. So it's pretty clear that if the speed of an object where no friction is involved is constant, if that object moves at constant speed, then no force is acting on it. The force acting on it is 0. So therefore, an object moving at constant speed will continue to do so forever if no force acts on it. Okay, that's an important concept. Okay, now consider a situation where mass M is acted upon by many forces. And let's assume that there's no friction involved and the mass is free to move in all possible directions. Let's say there's a force F1 acting along the x direction. And let's say there's a force F2 acting along the y direction. Well, so the question is where how will the mass respond? Where will it go? So we have to calculate the total force acting, which is F1 plus F2. How do you add these two vectors? Well, I made the example really simple, So we have a case where F1 is over here, a certain size, and then F2 is different size over here. So we know from before, I assume you have all been taught, that you add vectors by putting one vector at the tip of the other and taking the sum. And it turns out that the size of the resulting sum is obviously F1 squared plus F2 square root. That's the size. And the question is, what is the angle that it will adopt? Well, this tells you right away, because the tangent of the angle theta will be equal to F2 divided by F1. So therefore, theta is the inverse tangent, or the arc tangent, of F2 over F1. So basically, the solution of this problem is that you add the square and take the square root of the F1 and F2 sizes, and you take the ratio F2 over F1 and take the inverse tangent. That gives you the angle at which the mass will move. And if you know the mass, if you know F, then you know that it'll give you m times a. So therefore, you know its acceleration. Divide half by m and it gives you the acceleration. So you know where it's going to go, and you know how fast the speed of it will change. Okay, now I want to talk about a situation that's a little bit more complicated to illustrate some finer points. So consider a situation where there's an incline. Okay. And this incline is at an angle theta 1 from the horizontal. And consider the case where there is, for now, make it a little simpler, no friction. And the mass is on the incline. So gravity acts on the mass. So we know that there will be a force downwards that gravity imparts, and that force will be Fg is equal to m times g, the acceleration of gravity. So okay, so we know that the force acts this way, but the motion is constrained in this plane. I have to tell you that. So there's no motion out of the plane of the incline. So the motion only occurs here. So the component of gravity that matters is a component that projects along the plane of the incline. So we can draw this little right triangle here. So I'm going to draw it this way over here, so to be more specific. So we have a little component of the gravity this way, and then there will be another component of the gravity the other way. So here's the right angle, and this is the triangle I just wrote, and this is the angle theta 1 over here, and this is m times the acceleration of gravitational acceleration, so mg. So this component here we don't really care about because I told you there's no friction. So how much the gravity actually causes the mass to press against the plane, I'm not going to include in the problem for now. So I'm only interested in getting this component here, which is mg times the sine. So mg times the sine of theta 1. So we have one force, mg sine theta 1. We know that that's the force that causes the thing to slip. Now, how do we know it's right? Well, think about the case where theta 1 would go to 0. That is, it would be flat. If that was the case, then the gravity would not cause the mass to move leftwards, right? It would cause only the mass to push down. But we said we don't care about how much it pushed down. So if theta is equal to 0, then you know that this force here has to go to 0 because the mass won't move. It's flat. So mg times sine theta 1 equal to 0. Sine 0 is 0. So you know that this is the right analysis, because then it would tell you that the component of gravity in the plane, if the plane is flat and horizontal, then would be 0. So this is a kind of a quick way to know that this analysis is correct. So mg sine theta 1 is component of gravity acting this way. So now if you put some other force here, it could be like F, that acts at an angle, let's say theta 2 over here. Well, we don't really care about how much it takes out the mass from the plane, because the motion is constrained in the plane of the incline. So we only care about the projection of it along the plane. So it would be F times the cosine of theta 2. So we have the total force acting on the object, mg sine theta 1, and that's acting this way, negatively. So we have to have a negative sign to it, because you have to be consistent. If one force acts one way, then the other force acts the other way, then they have to be opposite. So this is acts, if this is 1 sub x in this direction, then there's a minus sign. Minus mg sine theta 1 plus f cosine theta 2. That's the force acting, is equal to m times the acceleration along the x direction. So that tells you that you can calculate how much the mass will accelerate this way by summing the components that line up in the direction of motion. I said there was no friction because if I had to include friction, then I would have to worry about the components that are perpendicular, because friction is a linear function of how much perpendicular force there is. So then I would have to worry how much force there is perpendicular to the plane of motion, because it would create a force that acts opposite the direction of the applied force. But in a case where there is no friction, then this equation is very simple. So, in recap today, I want to go over the most important points. So, we learned about Newton's first law of motion. F is equal to m times a. And I told you that it's a relationship between two vectors, a linear relationship that depends only on the properties of the object that's being, the force is being applied to, but depends on its mass. So a force causes the mass to accelerate, and the amount of acceleration that imparts to the mass depends on F divided by the mass. It depends on the mass. And I also told you that this is equal to the change in momentum over time. So it's clear that the force causes acceleration. Acceleration is delta V over delta T. Therefore, the mass changes speed, therefore it accelerates. And this causes the momentum to change. Okay, that's number one concept. Number two is units. The units of the force is Newton, the units of mass is kilogram, and the units of acceleration is meter per second squared. So the unit of the Newton is a kilogram meter per second squared. And then to solve problems, you take the vector sum of force components and you compute the resulting vector, and that gives you the force. And the vector, remember, is a quantity that has size and direction, so you need to worry about the size of it and the direction that it points into, and you divide by the mass. It will give you the acceleration, such that